Good afternoon. Just picking up what we have been looking into regarding functions, and just for what we have had from sections 1.3 and 1.4. Okay, we cross over to looking at equations in two variables, especially in the xy coordinate system, and among the topics we looked at included slope. And just for the group that we have from section 1.4, okay, and we have with say in numbers 27 and 30, okay, we're looking at the determination of the slope of the line that passes through the given points, okay. And again, we have with 27, okay, we have ordered pairs with 17.9 and 42.6, and we have those as two among infinitely many other points through which that particular line is going to pass. And looking for the slope of this line, okay, first of all, we can determine, okay, what we will have designated for the first and second x and y values. Okay, so we have with 17 and 9, okay, we'll let this be the first set of x and y terms. And with 42.6 provided subsequently, okay, we'll just have this as the second set. And for what we have in the case of 27, okay, so we have with the slope formula, again, you have the slope m is equal to the change in y with respect to the change in x, okay, and often that is denoted as y of 2 minus y of 1 all over x of 2 minus x of 1, okay, such that x of 1 and x of 2 are not equal to each other. And looking at crossing over to substituting, okay, so we have for y of 2 minus y of 1, okay, so we have y of 2 is at negative 6, and we have minus y of 1, okay, so we have negative 9. For x of 2 minus x of 1, okay, we have 42 minus 17. And just looking at what we have in continuing, okay, so we have negative 6 minus 9, okay, so that would be negative 15. 42 minus 17 is at 25, okay, so you have the collective vertical change of minus 15 units, and the collective horizontal change we have at 25 units. And for the determination of the slope, okay, we have this ratio can be simplified, okay, and so for what we have with negative 15 and 25, we will have the greatest common factor at 5. So you can say we have negative 15 is negative 3 times 5, and 25, again, it's going to be 5 times 5, and we can have the set of 5s to cancel out. So we have for the slope of the line described in number 27, okay, that is going to end up at minus 3/5. Okay, and for the next item, okay, we have in number 30, okay, so you have ordered pairs, okay, that have rather large absolute values for the coordinates. Okay, so we got negative 100, negative 16 for the first point. Second point mentioned, we have 84, 30, and just sort of reapplying in identifying what will be the first and second x and y terms. And again, just keeping in mind that all ordered pairs are of the form xy, so letting negative 100, negative 16 be the first point. So we have x of 1 represented by negative 100, and y of 1 represented by negative 16. And so for 84, that will be the second x, and 30 will represent the second y. And looking at what we have, okay, in utilizing, once again, the slope formula. Okay, so again, you have change in y with respect to change in x. Okay, so for crossing over into the substitution stage. Okay, so you have y of 2 minus y of 1. Okay, so that's going to be 30 minus negative 16. And for x of 2 minus x of 1, okay, so you're going to have 84 minus negative 100. Okay, and here I have a pair of subtractions of negative terms. I could have applied pluses, okay, to the subtraction and to the negatives, but I'll just carry this on over here. Okay, so we got what will translate to 30 plus 16 over 84 plus 100. Okay, so right now we got 46 over 184, and this ratio can be simplified. And what I will do here, I'll just sort of do this incrementally. Okay, so we have 46 and 84, those are even values. So for 46, okay, that will be 23 times 2. And 184, okay, that is going to be 92 times 2. And we can lower this ratio even further, okay, because it turns out that 46 is a direct factor of 184, and just with the incremental reduction case you have for 23 over 92, and it's going to turn out that 92 is going to be a direct multiple of 23. For 92 is going to be 23 times 4, and in the same vein, it would just so happen that 184 is 4 times 46. It just for what we have here for the next reduction, so we have 23 to cancel out, and so for this particular slope, okay, we have the reduction all the way down to 1/4. All right, and just looking at the determination of slope, not only from given order pairs, but from graphs. Okay, and you can attain the slope either through finding a couple of points and applying the slope formula, or also if you happen to have the graph to be drawn according to scale, it could do something along the lines of what's essentially counting squares. And for what we have in the case of number 38, okay, and we'll just look at this one case. So we got a line that is sloping upward, and what we can do here is that we can, so we have a grid pattern throughout, and what I can do is that I can find, let's say, some points here where you have a common, so you have intersection, so you have like -2, 0, and also where you have intersection of grids. Okay, you have here, and also on the y-axis. And just looking at what we have, say going from -2, 0 to, let's say, the y-intercept is 0, 1. And we have for the pattern, okay, so if I go up from -2, 0 to 0, 1, so I can go up 1 unit and then shift over 2 units. And if I go from 0, 1 to, well, it's like 2, 2, and we have going up 1 unit and shifting over to the right 2 units, okay, and I can just maintain the trend, okay, even from before the intercept. Okay, so you have a kind of like a staircase pattern. Okay. Okay. So we'll have for the slope itself. Okay, you're looking at the vertical change with respect to the horizontal change. And so just for what we have from a visual perspective, okay, so the vertical change would be the elevation of 1 unit. And for the horizontal change, okay, had increments of shifting over to the right 2 units. And so for that particular slope, okay, this will come out to 1/2. And for what we have in the case of number 39, okay, now here we have, instead of upward motion, we have gradual downward movement. And so if I were to look at the grid patterns, okay, and say if we have we have intersection, looks like we'll have one at -3, +3. We have also on the y-axis, and we'll have like another staircase pattern. So if I go from -3, 3 to, let's say, positioning level right now with respect to the y-intercept, so it's like I'm going to go down 1 unit and shift over to the right 3 units. Okay, so for this change, okay, so I have going down 1 unit and shifting over to the right 3 units. So we have for the slope, okay, again, you have a ratio of change in the y value, or the vertical change. With respect to the horizontal change, okay, so you go down 1 and move to the right 3 units. And for this slope value, okay, that is going to be a -1/3. Now let's say that if I were to include what we have in number 40, okay, here you see where we have sort of the grid patterns to intersect. Okay, so it's like we have a y-intercept to be such an occurrence. And if I go down and look at where the next grid pattern will have an intersection with the line, it's like it's going to be over here. Also have at the point, at the tip of the arrow. And so we have in this pattern, okay, so if I start from the y-intercept, so we're going to be going down and arriving at where we have level with the next point located. Okay, so we have shifting over to the right. So I've gone down 1, 2, 3, 4, shifted over 1. And see if I have consistency here. So going down 4, shifting over 1. And so I have in this pattern, so going down 4 units for every rightward shift of 1 unit. Okay, so we got here. So we got ratio of -4 to 1. So we have a negative integer slope value. Okay, so this will come out to -4. All right. Now, for what we have in the case of number 42, okay, here we have a vertical line. And again, a vertical line would fail the vertical line test, okay, because a vertical line is going to have like an infinite number of intercepts that would intersect with like another vertical line. And for what we have here, for a vertical line, there's no change in the x value. And because there's no change in the x value, you have like in your formula, x2 minus x1 would be 0. And that would lead to the slope ending up as an undefined value. So for all vertical lines, there's no defined slope. Now, and looking at what we have for the types of equations involving slope, and we have for the next item, okay, it says to express the given equation in slope-intercept form if possible, and then determine the slope in the y-intercept, and it says then to graph the equation using the slope and y-intercept. Okay, so again, we have with the slope-intercept form, okay, so this is going to make reference to y is equal to mx plus b, where m is the slope and b is going to be the y-coordinate of the y-intercept. Okay, so for what we have in number 52, now we've got an equation in standard form where we have both x and y are on the left side of the equation. And what I want to do is isolate y. And right now I have the y term to be negative y. Okay, so I can proceed. Okay, so if I'm going to get y by itself, okay, so first of all I'm going to get negative y exclusively on the left, so I can move the x term over. Upon doing so, I'm going to have negative y and getting as close to the slope-intercept form, so I'm going to have the x term out at front. So I have negative y is equal to negative 3x plus 6. And if I multiply or divide by negative 1, so I'm going to have the sign values to change. Again, you can just change all the negatives to positives right away, and vice versa. Okay, so changing the sign values. Okay, so we have y is going to be equal to positive 3x minus 6. Okay, so this is going to be the slope-intercept form of the line defined by the given equation. Okay, and so with the slope-intercept form, okay, we have for the x term coefficient, that is going to be the slope. So the slope is equal to 3. And for the negative 6 that follows, okay, that is going to be referencing the y-intercept. So we can say we have the y-intercept, you can say is going to be like in Alex terms, you have y is equal to negative 6, and as an ordered pair, we have 0, negative 6. Okay, and for a slope of 3, you can say that for a slope of 3, so you're looking at a pattern. Think of like a 3-to-1 ratio where you have like going up 3 and out to the right 1 unit. Okay, and looking at graphing the equation using the slope and the y-intercept. Okay, so we got the y-intercept. Okay, so we're going to have at 0, negative 6. And for the slope, okay, we have a slope of 3. So we can start a cycle of going up 3 units and shifting over to the right 1 unit. So if I go up 3 units and out to the right 1 unit, we have the order pair, say a 1, negative 3. And say if I go up 3 more units and out to the right 1 unit, I'm going to be on the x-axis, where that x-intercept is going to be 2, 0. And looking at constructing the line. Okay. And so we'll have, again, this straight line will be representing the equation where we have its slope-intercept form to be at y is equal to 3x minus 6, as well as what we had originally with 3x minus y, is equal to 6. All right. All right. So we have in this one, okay, so again, so we're maintaining a pattern going up 3 units and shifting over to the right 1 unit. And again, we have passing through the y-intercept, which we have at 0, -6. All right. Now, for what we have in the case of number 62, now we have fractional coefficients for both of the x and the y terms. And again, it is the object or the objective to get this in terms of y equals. Okay, and now for what we have in this particular equation, now we can take care of the fractions, kind of like what we did with rational equations. We can take care of the fractions if we multiply the terms all out by the least common denominator. And the smallest number that both 3 and 4 will go into, okay, that is going to be at 12. And so if I rewrite, okay, the terms that we have, we're going to have integer valued coefficients for the x and the y terms. Okay, so just looking at what we have in this situation. Okay, so if I clear out the fractions, so I got 12 times x over 3. 3 will go out, and 3 into 12 is 4. For y over 4, and get 4 to go out, and 4 will go into 12 3 times. And we have in the rewrite, okay, so you're going to have 4x plus 3y is equal to 12. And getting the y term by itself, okay, so right now we have 3y. Okay, so I can move the 4x over. And getting closer to the slope-intercept form, so I got 3y is equal to -4x plus 12. And we have with division by 3. Okay, so 3y over 3, okay, that's going to become y. And for the x term case, we have y is equal to -4/3 of x. And 12/3 is going to be 4. Okay. And just for the characteristics, okay, so the x term coefficient is going to be the slope. And for the y-intercept, okay, and again, so for the y-intercept, okay, your b value is going to be at 4. So we can say the y-intercept is going to be y is equal to 4. And as an ordered pair on the y-axis, okay, we'll have at 0, 4. Okay, and in terms of the pattern created, okay, with the slope, okay, so we're going to have with -4/3, okay, in terms of motion, okay, we'll be looking at a pattern, okay, so for -4/3, reading the graph from left to right. So you had the pattern moving down 4 and to the right 3 units. Okay, and just setting things up. Okay, utilizing the slope as well as the y-intercept. Okay, so the y-intercept we have on the y-axis at 0, 4. And if I go down 4 units and shift over 3 units, so we have an x-intercept at 3, 0. Okay, and I could actually continue the trend. So I got down 1, 2, 3, 4, and shifting over to the right 3 units. Okay, so we'll pass the number labeling, but your x value will be at 6, and the y value will be -4. And if I had any prior points, see, that would be -3, +8. Again, so you have pattern down 4 to the right 3 throughout. And again, the y-intercept we have at 0, 4. And again, this line will represent both of these equations. And once again, the slope-intercept form, we have it y is equal to -4/3 of x plus 4. Now, a situation where we have, well, it's going to be referencing average rate of change, which will be one of our topics in the near future. And we have in the illustration, okay, it says to find the slope of the secant line, okay, that is pictured in red, okay, and for the ebook it looks like it has kind of a violet color to it. Now for what we have for the secant line, okay, it's talking about this particular straight line, and it's cutting through, okay, this curved pattern at the points 1, 6 and 5, 2. And now you could look at the slope from either using the coordinates of the intersection points, which we have at 1, 6 and 5, 2. You can just have like 1 and 6 will be the first x and y values, and letting 5, 2 be the second ordered pair. Okay, so we have with y02 minus y01. Okay, so we have 2 minus 6 all over 5 minus 1. And 2 minus 6, okay, we have at -4. 5 minus 1 is 4. And so in this case, we have a -1-to-1 ratio. So the slope, okay, that is going to end up as -1. Okay, and you can do that through the use of the ordered pairs, but also you could also take what we have. Okay, so we had going from 1, 6 to 5, 2. And just in the big collective activity. So you have a drop of 4 units. And you have a shifting of +4 units. Now we still have like a -4-to-4 ratio would come out to -1. Okay, so just for the slope at -1, so just looking at what we have incrementally. Okay, see like a pattern, like going down one, shifting over one unit. Like counting the little squares as opposed to the bigger block sections. It's got -1, +1, and through that pathway, instead of the collective drop over the collective shift, incrementally dropping one, shifting right one, gradually. So you have like from 1-6 to 2-5 to 3-4 to 4-3, and you still had that pathway to 5-2 and still remaining on that secant line. So in this particular case, you can see I have -1 to +1. So once again, we have the vertical shift with respect to the horizontal shift, and through that perspective, you still come out to the same result. Two different ways of saying the exact same thing. All right. And now, just in the crossover, okay, for what we have, not only with single equations, but looking at relationships, okay, between lines. And for what we're going to be looking into, okay, is that for the next portion, okay. And this is going to tie in the formulas from the other day. And for what we have concerning parallel and perpendicular lines, okay, and just some definitions here. For parallel lines, okay, parallel lines, okay, those are going to be distinct as in different from each other. You had distinct non-vertical lines. That are going to have the exact same slope. And will never meet as in intersecting or coming to a contact point. And just examples of what we have for parallel lines. You know, say we have something like y is equal to 4x minus 3, and y is equal to 4x plus 7. Okay, so both of these lines, okay, have their equations, okay, expressed in slope-intercept form. Okay, so you got y is equal to 4x minus 3, and we have y is equal to 4x plus 7. Okay, so you have a lot of same characteristics, but notice we have different y-intercepts. So these lines are distinct from each other. Okay, And so for, if you notice, okay, for this pairing, these lines are going to have the same slope. And since they're not the same lines, but they nonetheless have the exact same slope, okay, these lines are going to be parallel. Now, another case. All right, let's say if we had that y is equal to negative 7/3 of x minus 2, and that y is equal to negative 7/3 of x minus 5. Okay, so not the same line since we have different y-intercepts. Okay, but we do have the same x terms, and so, and with the equations expressed in slope-intercept form, again we have history to repeat, where this time we have the same slope, and the slope for both of these lines will be at negative 7/3. So you have in this pairing, okay, the lines are parallel. All right. Now, in the case of, okay, so parallel lines, okay, there will be different lines, but different lines that have the exact same slope. Now, for what we have in the case of perpendicular lines, okay, now for perpendicular lines, okay, you're going to have lines whose slope values are going to be opposite sign reciprocals. And an identifying characteristic would be, okay, if the values are opposite sign reciprocals, you have the product of the slopes of the first and second lines will come out to -1. Okay, so you have lines whose slope values are going to be opposite sign reciprocals, and they are going to meet, unlike the case with parallel lines. And that will meet at a 90-degree angle. And let's say that if I kind of go with most of the earlier pairings for the parallel lines and just kind of construct a situation where we have perpendicular. Okay, so we got for these just a couple of modifications. Okay, so we have in these two examples, okay, just once again have, like from the parallel, just have the, in example 1 have the first line to be y is equal to 4x minus 3, and the second had the first line at y is equal to negative 7/3 of x minus 2. Okay, so again, we had with the first line, okay, the slope again was at 4. But now for the second line, okay, I want the slope to be an opposite sign reciprocal. And in this particular case, right, so the first line has a positive slope, and for the other line, I want the slope to be negative. And not just a negative, but an opposite sign reciprocal. So I'm not looking at -4, but the negative of the reciprocal of 4. So think of 4 as like 4 over 1, and the reciprocal of 4 over 1 is going to be 1 over 4. And so opposite sign reciprocal of 4 will be negative 1/4. Okay, and so you can just take like the product of the slope values for each line. So the first line, okay, we've got the slope value at 4, and the other line, you have the slope value at negative 1/4. 4 times negative 1/4. You got a positive times negative is a negative, so you have negative 4/4. And again, the product reduces to -1. So the product of the slopes we have at -1. And so we can say that these lines are perpendicular. Now for what we have in the next case, right? So we have for this first line, again, the slope was at negative 7/3. Okay, and to have the next line to consist of the characteristics that will have it to be running perpendicular. Okay, so for the slope, I'm going from a negative to a positive, and we're looking at the positive reciprocal of 7/3. Okay, so this will come out to 3/7. So in the case of the pairings, okay, so the first slope is negative 7/3. And for the second line, okay, so we come out to 3/7. Of course, negative times a positive is a negative. And you got 21 over 21, and the reduction goes to -1. So with the slopes ending up with a product of -1, it turns out that this pairing consists of lines that are perpendicular. All right. Now, for what we have in working with parallel and perpendicular lines, and we have for this particular portion, okay, so looking at determining equations of parallel and perpendicular lines. Again, just and we'll be using the formulas from the other day. Okay, so we have again, we have with the point slope formula. Okay, y minus y1 is equal to the slope m times the quantity of x minus x01 and for the slope-intercept equation, again, you see y is equal to mx plus b. Okay, now let's say that if we were to determine the equation of the line and we'll start out with parallel lines. Okay, so we have determined the equation of the line that runs parallel. Actually, what? Let me do this. Let's say I have it to run through a particular point. Okay, we'll say we have to go through let's say we have this parallel to the 2x minus y is equal to 10. Okay, so we have in this particular case, right? So you're looking at the equation of line that's going to run through 2, 7, and it's going to be parallel to 2x minus y is equal to 10. Okay, so we have in the procedure, okay, now we'll be looking at getting and not just the equation of the line. Wish I had put this out further, but there we go. Determine the slope-intercept equation of the line that runs through 2, 7 and is parallel to 2x minus y is equal to 10. Okay, so we have in the procedure, say if I'm looking for the slope of the given line, so for the given line, okay, so I have 2x minus y is equal to 10. Okay, so the line that I have is in standard form. Okay, and if I put this in the context of the slope-intercept form, it's going to be looking at isolating the y term. And so here we're going to have that negative y is equal to negative 2x plus 10. And for this equation, okay, so if I multiply or divide by negative 1, and that's just to change over the negative terms, including negative y to positives and vice versa. And so in doing this, okay, so for the given line, okay, we'll have the slope-intercept form, where in this case we had that y is equal to 2x minus 10. All right. So in this case, right, we have the slope value is going to be a positive 2. All right. Now we're looking for the slope-intercept equation of the line that's going to run parallel. Again, parallel lines are going to have the same slope. Okay, so the given line has a slope value of 2. And for the same slope, okay, for the parallel line, okay, have the slope is equal to 2. And in terms of setting things up, okay, through the point slope equation pathway, okay, now the parallel line is going to run through 2, 7. Okay, so the slope and a point through which the parallel line passes, okay, those are known. And so in the pathway to get to the slope intercept, I can start out with the point slope setup. Okay, so again, so we have with y minus y of 1. Again, so we have with our point through which the parallel line passes, okay, so y of 1 is going to be at 7. And the slope, again, that is going to be at 2. And for x minus x of 1, okay, so x of 1, okay, is going to be at 2. So x minus x of 1 translates to x minus 2. Okay, so this is going to be the point slope equation, but I'm looking for the slope intercept. Okay, so looking at the follow through, okay, so we have y minus 7 and distributing 2 over the quantity of x minus 2. So we have 2x minus 4. And to get y by itself, okay, so I'm just going to add 7 to both sides. And we'll have that y is equal to 2x plus 3. Okay, so that has a slope of 2. And you can check for the consistency. Okay, so with x and y at 2, 7. So if I go back, so like if y is at 7, left-hand side of this equation is 7, and I want the right-hand side to be as well. And while y is 7, we have x at 2. And 2 times 2 is 4. 4 plus 3 is 7. 7 is equal to 7. And so that equation will check out. All right. Now, so this is a case of what we have with a parallel line. And now let's say we have in the change up. Okay, so got the slope-intercept equation of the parallel line. Well, let's say if I'm looking at, say, passing through the same point, and I'm working with the same given line, but where this time I'm going to have the line to be perpendicular. Okay. And what we did before for the given line, I'm just going to duplicate this. Okay. So again, the given line, okay, has a slope of 2. And for the perpendicular line, okay, so again, we just have kind of use a little symbolism. Okay, perpendicular lines will have opposite sign reciprocal slope values. OSR, opposite sign reciprocal. Okay. And again, so we have the slope of the given line is at 2. So for the perpendicular, opposite sign of a positive is a negative, and the reciprocal of 2 is going to be 1/2. Okay, so the perpendicular line has a slope of negative 1/2. Okay, so again, the product of the slope values ends up at -1. 2 times -1/2 is -1/2. Now, we're looking at the line passing through the very same point as was the case with the parallel line. Okay, and looking at the slope-intercept equation of the perpendicular line. So again, just going through the point slope formula startup. Okay, so we've got y minus y of 1 again. So we have y minus 7. And this time, instead of 2, we now have -1/2 for m. And you have times the quantity of x minus 2. Now again, except for m, okay, everything else is the same as was the case with the parallel line. Okay, so looking at setting things up. So I got the point slope equation. Now I'm looking for the slope intercept. So I'm going to distribute -1/2 over the quantity of x minus 2. So we can say we have y minus 7 is going to be equal to -1/2 of x plus 1. And getting the y term by itself. So I can add 7 to both ends. And so we have in the results, okay, for the slope-intercept equation, so we're going to have y is equal to -1/2 of x, and 1 plus 7 comes out to 8. Okay, and you can check for the consistency. Okay, so you got the slope at -1/2, and with x and y respectively at 2 and 7. Okay, so left-hand side of the equation is at 7. Once again, I want the right-hand side to be as well. So we got 2 for x. -1/2 of 2 is going to be a -1. And -1 plus 8 is also at 7. So that would be the slope-intercept equation of the perpendicular line that is described. Okay, and let's say in this case, so say we determine the equation of the line that runs through let's say we have going through let's say we have going through 3, 11. and is. Okay, we'll see what we have first of all. We'll say we have to be parallel to 3x plus y is equal to 2. And we'll say for the second line, okay, so we'll have that to be perpendicular also to 3x plus y is equal to 2. So for the next few moments, and let me do this, fell into that trap again. Yeah, so for both parallel and perpendicular lines, okay, they're going to run through 311. And let's see what we get for the slope-intercept equations, okay, where we have parallel to 3x plus y is equal to 2, and also in the other case where we have to run perpendicular to also 3x plus y is equal to 2. So let's see what we get for the parallel and the perpendicular lines slope-intercept equations. Okay, if you're still working on these items, that's quite okay. Okay, again, we're looking at the slope-intercept equations for the parallel and perpendicular lines described. And to be able to get to those equations, be able to determine the slope of all the lines concerned, including the given line. Okay, now for the given line, okay, we don't have that in the slope-intercept form yet, okay, but we do have the standard form, okay, whereupon we have 3x plus y equals 2, and to translate the given line equation, okay, to its equivalent in slope-intercept form, okay, so I can isolate the y term. Then we have taking out 3x from the left. Okay, so we had that y is equal to negative 3x plus 2. Okay, so for the given line, okay, the coefficient of the x term is going to be the slope. In this case, so we had the slope of the given line is going to be at negative 3. And for the parallel line, again, parallel lines are going to have the same slope. So the slope is going to be at negative 3. And again, for the parallel line, the point through which it passes will be 311. And we'll get to the point slope equation for that one. But I just want to create also the backdrop for the perpendicular line. Okay, it's going to pass through the same point as is the case for the parallel line, but now for the slope, we're looking at the opposite sign reciprocal of negative 3, and so that's going to be a positive 1/3. Okay, and looking for the slope-intercept equation of the parallel line. Okay, so through the point slope equation route, okay, so you have y minus y of 1 is equal to the slope m times the quantity of x minus x of 1. Okay. And with the known values for m as well as x of 1 and y of 1, if I substitute accordingly, okay, so we have y minus y of 1. Okay, so that is going to translate to y minus 11. And we have the slope m again is going to be at negative 3. And we have times the quantity of x minus x of 1, or x of 1, we have at 3. All right, and looking at what we have from the point slope equation and getting it over to the slope intercept. So if I look at distributing negative 3 over the quantity of x minus 3, so we're going to have negative 3x plus 9 and getting the y by itself. Okay, so we have adding 11 to both sides. Okay, so we have y is equal to negative 3x plus 20. Okay, and so just looking at the consistency, okay, so we got the slope at negative 3, and seeing if 311 belongs, okay, so we have y at 11. So the left-hand side of the equation is going to be 11, and I want the right-hand side to be as well. So for the numerical value of what I have on the right, negative 3 times x will be negative 3 times 3, which is negative 9. Negative 9 plus 20 comes out also to positive 11. Okay. Now for what I have in the case of the perpendicular line, again, say I had the slope at 1/3, and just sort of restating product of the slopes given the line with a slope of negative 3. Perpendicular line have a slope of positive 1/3. So you got negative 3/3 again, which goes to negative 1. All right. And now utilizing again the point slope equation route to the slope intercept equation for the perpendicular line. Okay, so substituting again accordingly. So we have y minus y1 again is going to be y minus 11 is equal to, now for the slope of the perpendicular, so you have a positive 1/3. This will be times the quantity of x minus 3. And now looking at distributing 1/3 over the quantity of x minus 3. So I'm going to have y minus 11 is equal to 1/3 of x. And 1/3 of negative 3 is going to be a negative 1. And getting y by itself. Once again, we're adding 11 to both sides, and for the perpendicular line, we have that y is equal to 1/3 of x plus 10. And again, so you have y is equal to 1/3 of x plus 10 as the slope-intercept equation for the perpendicular. And just again, just double check the accuracy. Again, we have y at 11. Left-hand side of the equation, just like for the parallel line, is at 11. And I want the right-hand side to be as well. So for the right-hand side value, okay, we got 1/3 of 3, which is 1. And 1 plus 10 comes out to 11. So we do have consistency. Okay, so y equals 1/3 of x plus 10 is the slope-intercept equation for the described perpendicular line. All right, and just a quick set of items. And we have been mentioning, okay, y-intercepts and briefly x-intercepts, especially when looking at graphing samples. And for what we have with the intercepts, and we have in the case of determining x and y intercepts. Okay, so just kind of mentioning some of the definitions here. Okay, now, once again, stating, okay, all ordered pairs are of the form xy. Now, whenever y is 0 and there is an x value, okay, we're going to have an x-intercept. And by definition, now for x-intercept, x-intercept is going to be a location where the graph is going to cross or touch the x-axis. And if you had to specify the coordinates, okay, so we have from here, in an equation, you're going to set y equal to 0. And solve for x. Now, in the case of the y-intercepts, okay, there'll be just a slight inversion of the terminology. Okay, now for the y-intercept, okay, this time it is x that is 0, and y as the general coordinate for the y-intercept. Okay, and so you're going to have the location where the graph is going to cross or touch the y-axis. And we have here, okay, so got the general coordinates at 0y, and in terms of specifying the y values, okay, so we're looking at taking turns along the lines of what to set to 0 and what to solve for. So you have in an equation, okay, so we'll set this time x equal to 0 and solve for y. And just cases of what we have with x and y intercepts. Okay, and we'll say that we have for the first case, right? We'll say we have an equation whereupon we have 2x plus 4y is equal to 12. So you got 2x plus 4y is equal to 12. So you have a linear equation. Okay, and if I'm looking for the x and the y intercepts, again, we have for the x-intercept, again, we have the general coordinates are going to be x0. And for what we have in the case of the y-intercept, again, we have the general coordinates at 0y. So utilizing the same equation. Okay, now looking for the x-intercept. Okay, so this time, okay, we have setting y equal to 0 and solving for x. Okay, and here we're going to have 4 times 0 is 0. And so left-hand side, okay, you already write this as 2x, and now we got 2x is equal to 12, and right away, with division by 2, we're going to have the x is equal to 6. Now, for what we have in the case of the y-intercept, okay, then we'll have x will be set to 0. So the left-hand side of the equation, okay, that is going to be 4y. In fact, you don't have to write 0 plus 4y. So here we have 4 times y is equal to 12, and with division by 4, okay, we'll have that y is equal to 3. Okay, and so for what we have in the case of the x-intercept, you can see we have x is equal to 6, which is like Alex's terminology, but in ordered pair expressions. Okay, so that is going to be 6, 0. Now for the y-intercept, in equation terms, they have y is equal to 3. And in ordered pair terms, okay, so the 0y, again, is going to become 0, 3. Okay, so we have two intercepts, one on the x-axis and the other on the y-axis. So just looking at what we have here. Okay, so it's like for the x-intercept case, so we have it 6, 0. And the y-intercept I have at 0, 3. And for the line that's going to pass through these 2 points. All right, so for this blue line, okay, so this would be inclusive of 0, 3 and 6, 0, and this is going to be the combination of all the x and y values such that 2x plus 4y is equal to 12. And again, that is including the x and y intercepts of 6, 0 and 0, 3. Okay, and for intercepts, okay, they don't have to apply to just functions or straight lines. You can also have another case, and we'll say that we have, say, something that is nonlinear or that is not a straight line. And we'll say that we have, let's say we have x squared plus y squared is equal to 16. Okay, So if I'm looking for the x and the y-intercepts, okay, so for the x-intercepts, I have the general coordinates at x0, and for the y-intercepts, again, I have the general coordinates at 0y. Okay, so looking at solving for x, okay, so again, have x squared plus y squared is equal to 16. Again, just for changing up. Okay, so I have x squared plus 0 squared is equal to 16. Now, 0 squared is 0. X squared plus 0 is going to be an x squared. And for the follow-through, now I can either set up this quadratic equation in standard form, or I can apply the square root property of equality. So I got x squared is equal to 16. And if I go from x squared to x, we have the x is equal to plus or minus the square root of 16. And so we have the x is going to be plus or minus 4. Okay, so we have in the case of the x-intercepts, so you have that x is equal to negative 4 as well as positive 4. And just in ordered pair terms, again, general layout, we have x0. And in terms of the points, okay, so we have negative 4, 0 and positive 4, 0. Now, for what we have in the case of the y-intercept or intercepts, again, it is now x, which is set to 0. And so we have 0 squared is 0. And so we come to y squared is equal to 16. And the follow-through will have a lot of similar history repeating. Okay, but this time I'm going from y squared to y. If I go with the square root property of equality, once again, and just as x comes out to plus and minus 4, y does likewise. So yeah, y is equal to plus or minus 4. So we have for the y-intercepts, you say y is equal to negative 4 as well as positive 4. And again, just in coordinate fashion. Okay, again, not negative 4, 0, 4, 0, but 0, negative 4. And 0, positive 4. And just kind of looking at this one, I think I can put this one in. Okay. So we have 4 intercepts. Okay, so we got negative 4, 0. Okay, we have 4, 0 on the x-axis, and for the y-intercepts, okay, so you have 0, 4. and 0, -4. Okay, so we have for this particular image, okay, looks like there might be a little bit of deformation, but for what we have here, okay, so this is going to be an equation, okay, of a non-function, and you're going to have 0, 4, 0, -4 for the y-intercepts, and -4, 0, 4, 0. Again, we have on the x-axis, okay. All right, so you can have intercepts, okay, for both functions as well as non-functions, and you might have one type of intercept and not have one or the other. Like some functions might have x-intercepts and not y-intercepts, and potentially vice versa.